Section 24.9, from molecules to solids. In this molecular orbital energy diagram, we use alpha to denote the 2p atomic orbital energy in a carbon atom. In CH2CH2 or ethylene or ethane, the interaction between the two p electrons or p orbitals from each of the two carbon atoms form two new MOs. So this MO has an energy of alpha plus beta. This one, alpha minus beta. Remember, both alpha and beta are negative. So alpha beta lies lower than alpha minus. Alpha plus beta lies lower than alpha minus beta. Over here, the range is 2 beta. When you have 4 atoms, it's 1,3-butadiene. You have 4 pi electrons. They occupy these 2 molecular orbitals. This is alpha plus 1.618 beta, alpha plus 0.618 beta, alpha minus 0.618 beta, and alpha minus 1.618 beta. So the range from the lowest energy MO to the highest energy MO is 3.22 beta. Again, this is a 1,3-butadiene molecule. We can add more carbon atoms to the chain. We can have CH2, double bond CH, single bond CH, double bond CH, single bond CH, double bond CH, single bond CH, double bond CH, single bond CH2. And we can make that even longer. So when we have a really large number of atoms, the range from the lowest MO to the highest MO is going to be 4 beta. So there's a limit to it. And now if this N is large enough, you have a polymer. You have a polymer. With what kind of formula? Again, it's CH2, double bond CH, single bond CH, double bond CH, single bond CH, double bond CH, etc., etc. And in the end, you have CH double bond CH2. So in the end. In that case, if you have N carbon atoms, you can form N MO orbitals, molecular orbitals. The lowest MO has 0 nodal surfaces. The highest energy MO has N-1 nodal surfaces. So from bottom to top, you have an increasing number of nodal surfaces. And then again, when you have a very large number of N, so when this N is large, you have a solid. Only because you have really long polymer chains. And the attraction between the polymer chains is large enough to overcome the entropy effect. Section 24.10, making semiconductors conductive at room temperature. The band gap of pure silicon is 1.1 electron volt. So it's impossible to have silicon to conduct electricity at the room temperature or even lower temperature. However, if you just add some phosphorus atoms into the silicon network, the conductivity is greatly enhanced because the band gap is reduced to 0.04 electron volt. So look at this, from 1.1 electron volt to 0.04 electron volt. 1 electron volt is roughly 96.5 kilojoule per mole. So look at here, you have roughly 100 kilojoule per mole, and over here you have only 4 kilojoule per mole. What about the KBT value at the room temperature? RT value at the room temperature. At the room temperature, 300 K times the ideal constant, you get roughly 2.5 kilojoule per mole. So this band gap is really close to the thermal energy. and this one is much larger than the thermal energy. So how is this possible to reduce the band gap of silicon significantly by introducing phosphorus? Well, it's pretty simple. I want to show you this network, the silicon network. When we replace one of the silicon atom with a phosphorus atom, now you have one additional electron. And this additional electron has very high energy because look at this phosphorus. It's surrounded by 9 electrons. So it's 1 over the octet structure. And because this electron has much higher energy, you form a new band in the molecular orbital diagrams. So you need to look at over here. So without this phosphorus, you have a large gap, 1.1 electron volt. With phosphorus, you form a very thin new filled, now I'm going to call this band because it's almost continuous. So over here. And the gap between this new band and the empty band is only 0.04 electron volt. Now it's really easy to excite electron from this filled band to the empty band. You can also replace a silicon atom with a boron atom. A boron atom has 1 fewer electron than silicon. When you have a boron here, it's surrounded by only 7 valence electrons. And that will allow you to form one additional empty band here, really close to the filled band. So by replacing a silicon with a boron atom, you can also reduce the band gap from 1.1 electron volt to a much smaller number. So from here to here. Now finally, why can't we just use pure silicon to conduct electricity? So the reason is simple. When a band is completely filled, you cannot excite the electron anymore. You have to have a partially filled band. So you will have to excite the electron from a completely filled band to the empty band for this filled band to be active, for the empty band to be active, for the electron to flow. All right, but again, for pure silicon, the gap is 100 kilojoule per mole. It's roughly 40 times the value of R times T. So it's really difficult to use the thermal energy to excite electrons from the filled band to the empty band. Now by adding phosphorus, we create a new filled band that's so close to the empty band. The gap is very close to the thermal energy, R times T. And then that makes it really easy to excite an electron from the filled band to the empty band. By replacing silicon with boron, we can create another empty band to reduce the gap.